Eric and Colin are working on grading your third work set. Your second work set's been graded now. And they said they'll have office hours from 12 to 3 tomorrow. And I'll be in my office from 3 to 4. So you've got ample opportunity to come and get a final, if you've got time from your studies. I don't know if you have time from your studies. How many are writing more than one midterm on Thursday? Oh, what does that mean? Half a midterm? Oh, okay. So if a student has been ill and wants to be excused from the midterm, and this is a genuine case and have a doctor's note, what do you think the remedy should be? So is it fair to say, okay, you can write the midterm on Monday, the same midterm? Who thinks that's fair? Who thinks that's not a good thing to do? Okay. So who thinks that if I say, okay, you've got a genuine excuse, you're on your back, you've got a doctor's note, what I'll do is I'll rescale your final to be equivalent to your final and midterm. In other words, whatever you get in your final will be scaled to give for your midterm. Is that a reasonable thing to do? Yeah? The final is probably from lectures 10 to 24 or something. It's 26, 10 to 26, yeah. So, I mean, the other thing, so short of setting a separate exam, which is really a lot of work, those are the two possible solutions. So if I were to say the two solutions are allowing the individual to take it late, the same exam, versus allowing the individual to take their final grade and rescale it to be equivalent to the final plus the midterm, who would go for allowing the individual to take it like 4 or 5 days later? So you've got to vote one way or another, which is the lesser of two evils, so to speak. So who would think allowing the individual to take the exam on the Monday? Can you put your hands up? 1, 2, 3, 4, 5. And who would think allowing the individual to have their final rescaled so that the total equal to the final plus the midterm? Okay. Okay. So that's what I'll do. So if you're desperately ill, but it's no good giving me a doctor's letter to say you were ill last week for 3 days. It's got to be ill this week for 3 days before the upcoming exam. And you're so ill that you can't relax in bed and study. That it's actually a condition where your brain is frying because your temperature is high. Okay. Any questions about the midterm? Yeah? Sorry, I'm not sure what you're asking. Yeah. Right, yeah. Okay, so I'll go over what you need to know. You need to make sure that you know the difference between discrete and continuous equations, how to write them down, the equilibrium conditions, and how to talk about the stability of the equilibria. And I have a simple table that you fill out in the handout, in the handout part of the exam. You need to review all the stuff on genetic models, and in diploid organisms, you get different phenotypes and genotypes. So you get every individual has 2 alleles in the simple model, big A and little a. So you need to know how to calculate probabilities and proportions of setting up the mating types, and what is the probability that a particular mating type will arise if the proportion of alleles in the population is at a certain value. So you need to know that stuff. You need to know the basics of the logistic model and harvesting ideas relating to the logistic model, which is the Gordon-Schaefer theory, and the Beverton and cohort analysis, and so there's the Beverton cohort analysis, there's the Schaefer theory, and then there's also the question that I gave you. Now, the question I gave you, it turns out, so when I wrote the article for the encyclopedia, I named the function V. In the textbook, that same function is named P. In the question, I called the function S. So that way you won't get confused with P and V. So just work with S in preparing your answer. And I know that there's some notational issues that Colin and Eric have clarified for you regarding that. So in the Faustman stand analysis, you have to know how to write down the present value for a single step, for multiple steps. When you write it down for multiple steps, you get that sum. You need to know how to manipulate that sum to get an expression in terms of e to the minus delta t times the function S. You need to know how to differentiate that and reorganize the terms to get the Faustman formula and interpret that and work that out for a special case. But you've got that now. I've given you that question. And then there's the Beverton, and then there's the modeling of the host parasitoid system and the interpretation of different functions and how to put that model together. That's basically everything that you need to know. And so I'm not going to give you all of that. I might leave out some of it. And I'm not saying which. And I'm not giving you a choice. Okay. Anything else? Yeah. Von Bertalanffy. Yeah, you do, definitely. Okay. And I'm not going to ask you to integrate the von Bertalanffy equation to get the answer. I'm going to ask you to differentiate the answer to show that it's equal to the equation. And I'm telling you all this and I haven't even been bribed with anything. Like imagine if you give me bottles of whiskey or something, what I would be saying now. It's too late. So I'm not going to say much more unless anybody has a legitimate pressing question. Okay. So what we're going to talk today is about phase lines and classifying equilibria. We're doing this a little more formally than we have, but we've talked a bit about this up till now. And I'm going to start with the logistic equation. I don't know if these will write, so I might have to use my own. Let's see, dy dt is ry 1 minus y upon k. So you'll notice sometimes equations are dx dt, sometimes they dy dt. You just have to get used to using different notations. Okay. So this equation, we're looking at y as a function of time. So how many equilibria are there to this equation, and what are they? And if you can't answer this now, you better be able to answer it by Thursday. Yeah? Okay, so you're heading for an A. And if I started out above this line with the initial condition, what would happen? If I started out over here, what would the solution look like? Okay, somebody drew it. And if I started out over here, let's say this is k upon 2. If I started out at k upon 2, what would the solution look like? Yeah? Okay, and what would the slope be over here? Right, but it would look like this. It actually turns out that this is where the inflection starts. So that if I start, let's say, at point 1k, then it starts out gradually growing exponentially. You have a point of inflection here. What does it mean to say I've got a point of inflection? How do you find a point of inflection? The second derivative is 0. Second derivative tells you about the rate of change of the rate of change, or the rate of change of curvature. And, okay. Now, I have time. Imagine I squashed time out of this diagram, and I just had an axis over here. I'd have 0, and I would have k over there. And now, what I could do is I could say, if I start above 0, I move down to 0. Sorry, if I start above k, I move down to k. If I start close to 0, I move up to k. So this tells me I move away from 0. I'm not looking at this over here for the logistic, but the other models where it may be meaningful for this variable to be negative. And I'm going to write down some models where it's meaningful for that to happen. But in the meantime, this line is called the phase line. And on the phase line, you draw arrows that tells you the direction in which the population moves. So the phase line is a way to talk about equilibria. So if we now have a look at what's on the board over here, or what's on the screen, if I could get the light over there, thanks. Okay, great. So to draw a phase line of the equation, draw a vertical line corresponding to the y-axis, draw solid circles on this line that correspond to the equilibria, draw an upward arrow on intervals where f of y, this side, is positive, and down arrows where f of y is negative. And that's how you would draw a phase line. Now in the next example, we consider the growth of two clonal populations of lizards. You all know what clonal reproduction is? Anybody? Huh? Okay, and does that help anybody if we say clonal is parthenogenesis, or is it more helpful to say parthenogenesis is clonal reproduction? Anybody else? It's what we're all dying to do, is to reproduce clonally. Make little copies of ourselves and populate the world. Unfortunately, we can't do this. We have to have sex, and we have to dilute our genes. This is something we don't like to do. But lizards are a population that can fulfill their dreams in this way. Clonal reproduction is a much more efficient way of getting your genes into the next generation. So there's a whole field of study is why did sex evolve? Anybody have any idea on that? To make life worth living? Yeah? Okay, to provide extra variation that you don't have in a clonal population so that evolution can take place, especially when you're trying to have an arms race where you're trying to outwit an organism that's trying to get you, like a pathogen. So pathogens evolve rapidly, and sex provides a way of making a variation in your offspring. And so different individuals have different traits, and some traits are going to be better than others at particular times. So there's, in problem 39, in problem set 6.5, there's a question which asks you to lead you through an equation, and you finally develop the equation, dy dt is r sub a, little a, and r sub big A, times y, 1 minus y. So that looks like a logistic equation with carrying capacity 1. But in this case, it's not just a little r that's positive, it's the difference between two r's. And so if you've got two clonal populations and they're each growing, or two populations of weeds, two populations of lizards, depending on their values of r, the one's going to be growing faster than another. If you have a look at y, being a variable that says what's the proportion of one type to the other type. So we have one type that we call little a, and one type that we call big A. And at any point in time, we can look at the population and we can say what proportion of the population is little a and what proportion is big A. And if you're looking at just the proportion of, I don't know if y is the proportion of little a. If y is the proportion of little a, that proportion can go anywhere from 0 to 1. 0 meaning that it's all big A, and 1 meaning it's all little a. Now, as these two populations grow, if one is growing slightly faster than the other, so if r little a is bigger than r big A, then the equation that governs this rate of growth of the change in proportions is given by this equation, r little a minus r big A. So if r little a is bigger than r big A, the proportions will increase. And if r big A is bigger than r little a, this is negative, the proportions will decrease. And the way to show that is to draw these phase lines. And in the one case, when you draw the phase lines, the arrows are moving away from 0. That's when r little a is bigger than r big A. And in the reverse situation, the arrows are moving towards 0 and away from 1. And so, in this case, obviously, the process is just between 0 and 1 because it's a proportion. The proportion can't be bigger than 1 or less than 0. So it's this part of the arrow that tells you what's going on and whether the population, which one is going to dominate. So this is actually an important principle. If two populations are very similar, they're doing the same thing, but one has a slightly increased intrinsic growth rate, then eventually it'll swamp the other population. The one that has a slight edge, this is the effect of compounding. If you had to take two amounts of money, you took $1, and one was growing at 4% a year in one bank, and the other was growing at 5% a year in another bank. After 100 years, the one that's growing at 5% will be many, 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 many times bigger than the one that's growing at 4%. Because there's this geometric effect, and so the ratio happens so that as this process goes on, all the money in the one bank will swamp the money in the other bank. Any questions about that? So we come to this idea of the replicator equation. And the replicator equation is a notion that came out of something called evolutionary game theory. And we're going to talk a little bit about game theory in particular after this. Who's heard of the prisoner's dilemma? Okay, and who's heard of the game tit for tat? Okay, so we'll talk about these a little bit. But before we talk about this, we're going to talk about the replicator equation, which comes out of evolutionary game theory. And in evolutionary game theory, Maynard Smith, who was from 1920 to 2004, is one of the most well-recognized names in evolutionary theory. So to people in the field, he's like, after a couple of people like Darwin and Hamilton, his name comes up as one of the most important theorists in evolutionary theory of the 20th century. And he developed this idea of the replicator equation, what's called the hawk-dove game. And in the hawk-dove game, you can imagine there are two kinds of individuals. So imagine there's a single species, and we call them humans. And in humans, there are two kinds of behaviors. There's behaving like a hawk and behaving like a dove. And we actually do this. We call politicians hawks or doves. So the hawks are very aggressive, and they like to fight. And the doves are not aggressive, and they like to cooperate. And so you get what's called a payoff matrix. And the payoff matrix is that if two individuals of type A meet, then on average, they each get a payoff PAA. And if a little a meets a big A, then on average, they'll get a payoff P little a big A, or P big A little a. And generally this is symmetric, because we're not saying who I name first is important. And then if two big A individuals, this can be the situation. So when we come to the hawk-dove game, you'll see that whenever a hawk meets a hawk, and they're going to fight over something like a resource that they want to use, they fight until one wins. And there's a certain value to getting the resource and a certain cost to fighting. Whenever a hawk meets a dove, there's no fight, the dove just goes away and the hawk gets the reward. Whenever two doves meet, they don't fight, and they just share the reward. So you'll see how this works when we set up the equation. But when you set up the replicator equation, we assume that the growth rate, little r, sub a, small a, and little r sub big A, these are how hawks and doves in the population will increase. And they will increase at a rate at which they can get these payoffs. So the more payoff you can get, the faster you can increase. And so we say, if there's a proportion y of type little a, and little a's meet with frequency with frequency y, then they'll get PAA. If little a's meet with frequency P, little a, big A, then the frequency with which they meet the big A individuals is 1 minus y, and this is the payoff that they get. And the same is true from big A's perspective. When big A meets little a in proportion y, big A will get a payoff PA, little a. And when they meet others of their kind in proportion 1 minus y, they'll get a payoff P, big A, big A. So if you go through this and you take the replicator equation and you write it down, and where you've got r sub little a and r sub big A, you put these values in, you'll get this equation, which is expressed in terms of these rewards that the individual gets. Okay, so we're going to come back to this. This is a differential equation that tells you about this replicator process. The ideas for setting up these kinds of equations goes back to the prisoner's dilemma. Let's make this a bit bigger. Okay. So the prisoner's dilemma is a canonical game analyzed in game theory. And it goes something like this. So two members of a criminal gang are arrested and imprisoned. And each prisoner is in solitary confinement with no means of speaking to or exchanging messages with the other. And the police don't have any evidence. The only thing they can do is cross-examine these two prisoners. And the police offer a bargain. You know, they say, if you talk, you can get off. And the other guy will be punished and go to jail. And so the idea is to make the prisoners talk. And the rules are that if A and B both betray the other, each of them will serve 2 years in prison. So if I betray you and you betray me, we each serve 2 years. If A betrays B and B remains silent, A will be set free and B will serve 3 years. And if A and B both remain silent, both of them will only serve 1 year. So in other words, if we say we're not going to talk, then there's not enough evidence to convict on the bigger charge, and each of them gets 1 year. If one talks, as a reward, they get off, and the other person goes for 3 years. But if they both rat on each other, they each get 2 years. So you don't know what the other guy's going to do, so what would you do? Yeah? Okay, yeah, because you could then, instead of going for 2 years, if you both keep quiet,